Let's look at some properties of definite integrals. So this first one here to start with, notice that typically I've been writing a as the lower limit of integration and b as the upper limit of integration. Well, this is connected to that. So here we have the integral from b to a. And it turns out that that is the same thing as -1 times the integral from a to b of the same function. Now, to think about why that's true, think of here that maybe I'll put this in dark blue. In this case, delta x would be a minus b over n, which would be -1 times b minus a over n. And of course, the b minus a over n would be the delta x for the second thing I have there. So that just shows that connection. If I integrate from a to a, so anytime you integrate from a particular value to that same value, you'll always get 0. Geometrically, you can think about that as the area of a line. And again, thinking about our definition, if you were computing delta x, you would get a minus a over n, which of course is 0. So this next one here is supposed to reflect that you're integrating a constant function. So the function f of x equals c. In this case, you will get c times, let me put this back here, b minus a. So again, what's important here is this is a constant. And a quick way to think about this is the geometric interpretation, right? If you had a constant function, and I was integrating from a to b, we said that we could consider the area under that curve, and that would be the area of a rectangle with side length b minus a and another side length c. So again, it's important here that c is a constant, but here we're looking at a constant multiple of a function f of x. So if I integrate my c times f of x, that's going to be equal to the integral, of c times the integral of f of x over the same bounds. So there's a couple ways you can think about that. For one, notice that the height of each rectangle will be scaled by that same c value. And that's another way to kind of consider how that has that effect on the total sum. But this is also a remnant of one of our properties of sigma notation that we talked about, being able to pull scalar multiples outside of the sigma notation. And then, of course, likewise, we can do that with limits. So that's how we can see the connection to the definition. If I'm integrating the sum of two functions, that's equivalent to the integral of the first function plus the integral of the second function. Again, that also stems from a property we looked at for sigma notation, being able to break up the terms within the sigma notation that are additive, like into two sigma notations, and then carrying through our similar limit property, which again connects that back to the definition of the definite integral. This last part I'll point out is a different kind of sum. So notice the integrand is the same in both of these integrals, but what's different is we're splitting this up the interval. So if I integrate from a to c, and then I integrate from c to b, it turns out this is the same thing as integrating from a to b. Now it turns out that this is true regardless of where a, b, and c lie with respect to one another on a number line. I think it's probably easiest to visualize if we had A, C, and then B, right? Imagine that this is my function. And we could, first of all, think about the integral from A to C and the integral from c to b, add those two together. That's what I have on the left-hand side. But importantly, that's the same thing as just integrating all the way from a to b. So because, like I said, it doesn't matter that they lie in this order, really you would still be able to verify this if you combine that with our first property, if you happen to be integrating something from, say, right to left. And then the last property I want to point out here is that if I have the knowledge, let me say, on the interval from a to b, if I know that f of x is less than or equal to g of x, then that implies that integrating over that same interval, if I integrate f of x, I'm going to get something smaller than if I integrate g of x. And again, you can think about the only distinction here would be the rectangle heights, and we would be able to compare those from the function. And likewise, think about the geometry involved. So here's A, here's B. If this is f of x and this is g of x, again, what we would be able to do here is compare the areas involved. So the area under f of x, and then we could see how that compares to the area all the way under g of x here. So these are going to be useful properties for lots of situations, but we can also use them more immediately to help us concretely evaluate certain examples. So if I have an example here where I don't know what f of x is, but I know the integral of f over the interval from 0 to 5 and from 0 to 8, let's use that to evaluate some related integrals. So for this first part here, we want to integrate 3 times f of x. Well, we know that from a property above, I can bring that 3 out front of the integral. And now this becomes a product where we know that I'm multiplying 3 by something that we're told evaluates to 4. So this becomes 3 times 4. And so I know, even though I don't know what f of x is, I know that this evaluates to 12. For the next part, we want to integrate from 5 to 8. Again, you can think about the kind of number line associated to this, that we're looking at, we know 0 to 5, and we know 5 to 8. And we want to we know 0 to 5 and 0 to 8, and we want to find 5 to 8. So this is going to come down to that sixth property we were looking at above. So I want to try to break this up. So the integral from 5 to 8, there's lots of ways I could go about doing this, but you could think of it as what we would get if we integrated from 5 to 0 plus 0 to 8. So to align this, I'm using property 6, where A is 5, B is 8, and I've chosen the C value 0. And so this is an example where I was saying this is maybe not the way we would visualize it with 0 not being in between 5 and 8, but I can still use it because this first one, the integral from 5 to 0, is negative the integral from 0 to 5. That's from our first property. And we know that the integral from 0 to 8 is 16. That's given. So now I just add to that negative 4, and we get our answer of 12 here. And then finally, integrating this sum, I can use the property that says we can break this up into the integral of 5 plus the integral of f of x. Whoops. And the integral of 5, think of that as our c value from property number 3. We take 5 times the length of that interval. And then the integral of f from 0 to 8 is 16. That's given. So we get 40 plus 16. We're going to get 56.